This conference will now be recorded.
Very good evening, students. Today we'll be discussing numerical problems on electrostatics. Basically, on the sections we have learned like how to calculate electric field in both ways using Gauss's law or using general formula for point charges, for continuous charges like disk due to solid sphere, etc. We have already learned. So we'll try to solve few numerical problems which are typically asked in various competitive exams or in CBSE board exams, etc. So today, okay, let us see with the first problem. So this problem is saying that a point charge Q is placed at the center of a cube. Suppose the medium in the center of the cube is air. What is the flask linked with all the faces of the cube? With each face of cube. So these are two problems, and as you can understand, this problem can be solved using Gauss's law. So this problem is from Gauss's law actually. Okay, Gauss's law of electrostatics. So this problem is from Gauss's law of electrostatics. Now, if you remember what is Gauss's law, then it is very fine. I just want to tell you once again, mathematical form of Gauss's law is given by E dot ds is equal to q by epsilon 0. Okay, if the charge is situated in the vacuum, okay, this is free space permittivity, as you know. So in this case, as I said, you can consider the medium inside the cube. Cube means this one. Okay, somewhat this. So this is a cube. If you keep a charge exactly at the center of the cube, so the charge is q. Okay, if you keep this q charge at the center of the cube, then what will be the flask? What is the flask linked with all the faces of the cube? So first of all, see, in this case, since the charge is q, so total flask will be q by epsilon 0, as you can understand. So total flask coming out of the cube is q by epsilon 0. This is first part. Suppose this is the principal idea of what we know from the Gauss's law. Now, you know, there are 6 faces for cube. 6 faces for cube. Okay. So 6 faces for cube you have. Now, since this is a symmetrical body and the charge is situated at the center of the symmetric body, then each face has equal probability to have flasks through it. Okay, each face has equal probability to have flask through it. That means if I have 6 faces, then the flask will be divided by, or flask will be shared equally will be equally shared by all six faces. All six faces. Okay. The flask will be shared by all six faces equally. That means what will be the flask? First of all, what will be the flask? Flask with all the faces linked. Okay. So with all the faces means for entire cube. So this is with all the faces. Then flux linked with each face means it will be shared by 6. So it has to be actually divided with 6. So this will be the flux through each face. So the total flux is Q by epsilon 0, which will be shared by each face. So this is very nice. Up to this is very nice. Now if the point charge is at one of its corner, what will be the answer for the part A and B? See, what is the question? Now the question is that question is this. A charge is now placed at the corner of a cube. Okay, then question is what is what is the flux through all the faces? Okay, and what will be the flux through each face? Each face of cube, okay, each face. So this is the question now. See how to solve this problem. See, if I have a charge at any one of the corners of a cube, then how do you get the total flux through all the surfaces? First of all, see, electric field from here will be symmetrically, since it is point charge, it will be actually electric field plus or electric field lines will be like this, isn't it? It will be going out, since it is positive charge I have supposed. So it will be actually symmetrically. It has this, so point charge has spherical symmetry, okay? Spherical symmetry. In all directions it will go. So then what will happen? Actually, some of the flux field lines will be entering to the cube and some of them will be just going out, isn't it? So some of the flux lines are going into the cube and some of them will be going out. Now by symmetry, actually by symmetry, see, if I have this charge at the corner and this, see, I can actually consider a big cube consisting of such 8 cubes, okay? In the sense I can say that this charge at the corner could be shared by 8 such cubes, okay? 8 such cubes. So side this 3, 4, another side up will be another 4. So each, see, this cube at corner of a cube will be equally shared by 8 cubes. 8 cubes. Okay, if it is equally shared by 8 cube, what will be the total flux through each cube or for this cube? So flux through entire cube, flux through the entire cube given is q by 8 epsilon 0, because q by epsilon 0 is the plus total flux, and that is shared by 8 such cubes equally. So that's why, see, the first answer is this one. Okay, so this is the first question. So total flux through the entire cube or by or through all the faces will be q by 8 epsilon 0. But how about the flux through each face? Flux through each face. Now at this place I have to actually think about the Gauss's law once again. See, it is given by E dot n cap ds or E dot ds, area vector. This is electric field vector. This is equal to q by epsilon 0. And see, in this case, you know, the three surfaces which is attached to this. See, this one surface, this one, another surface, this one, and the other surface is this one. This adjacent three adjacent faces. Okay, three adjacent faces. You can see here the electric field. I can say electric field will be actually perpendicular, okay, perpendicular. I'll just write in phrase. Okay, I'll write firstly. So electric field or electric flux through three adjacent faces will be 0. Why? Because for those, okay, electric field because E and ds vectors will be perpendicular to each other. Okay, perpendicular to each other for those faces. For those faces. So this is the reason why the flux will not be equally divided by 6 faces. Okay, in this case, see, you might be very casually doing this answer, that q by 8 epsilon 0 into 1 over 6. This is not the answer actually. This is not the answer. because through three phases there will be no flux. This flux will be actually shared by three phases alone. Okay, other three phases will be actually, see, other than the adjacent phases, so other three phases will be sharing the flux through them. Okay, what are those phases? So this is one phase, bottom one, and another one is the side one. Okay, this one. So these three phases will actually share the flux. These three phases, and another one is this one. Okay, these three phases will share the total flux. So total flux is Q by 8 epsilon 0. So flux through each will be Q by 8 epsilon 0 into 1 over 3, because it will be shared by three phases. Okay, I have shown you in this. See this one, the bottom one, and then this one, and this one, the vertical one, this sidewise vertical. So these three phases will actually share the total flux. So the flux through each phases will be then, each of these three phases will be then 1 over 24 epsilon 0 q into 1 over 24 and epsilon 0. Okay, so this is the flux through each phases. Through each phase in the sense through each of the other three phases. That is the thing. Now we'll go to the next question. So this is also very interesting question. This question says, two infinitely long parallel conducting plates having surface charge densities plus sigma and minus sigma respectively are separated by a small distance. Kind of this. So one phase, another one is this one. Okay, so these are two infinitely long parallel phases, say. Okay, so one has positive charge sigma plus sigma charge density. This is surface charge density, and this is negative. And we are not going by my drawing. I'm just considering these two plates are identical in shape or dimension. Okay, so they are actually separated by a small distance. Let us say that small distance is small d, and these are actually two vertical infinite planes, suppose. And the medium between the plates is actually given as vacuum. So this is vacuum air or vacuum, I can say. Epsilon 0 is the dielectric permittivity of the vacuum. Then electric field in the region between the plates. Okay. So here I have to find out what is the electric field. So electric field region between the plates, I have to find out. So there are some options. I'll just write it down here. So first option is says, it is saying first option is 0 volt per meter. Then second option says it is sigma by 2 epsilon 0 volt per meter. And option C says sigma by epsilon 0 volt per meter. And option D says 2 sigma by epsilon 0 volt per meter. So these are options for this question. So, if you remember from Gauss's law, Gauss's law for infinitely or infinite plane sheet. plane sheet. Okay, do you remember this? Okay, I'll just give you the formula. So the electric field created by an infinite plane sheet, if it has positive, okay, let me write. So electric field produced by such plates or plane sheets will be given by sigma y to epsilon 0, and it can be plus or minus. If it is positively charged plate, then it will create positive sigma y to epsilon 0. If the plates are negatively charged, then the field, electric field, will be minus to minus sigma y to epsilon 0. Now for this, at this middle point, what will be the flux? One more point I would like to tell you that, see, if I have, let me take infinite plane sheet is this one. Okay, so plus or minus, whatever it is. So at any distance, electric field will be just sigma y to epsilon 0. It is not going to die out. It is not going to die out. Even in this direction also, at this point, the field, electric field strength will be sigma y to epsilon 0. Okay. At this point also, it will be sigma by 2 epsilon 0. It is not dying out, or it doesn't have any distance variation from the plate. But one thing we need to remember, that if this is positively charged, then it will be positive here. If it is negatively charged, then it will be negative here. Okay. So positive here, negative, positive here, if it is positively charged. Okay, suppose I have here both are not positively charged. One has charge negative. So at this position, at any distance in the middle point, see this charge or this plate, positive plate will create a field sigma y to epsilon 0. I am just considering this point, and this negative charge will actually produce negative to sigma by epsilon 0. All right. Okay. In this case, I'd like to tell you one more thing. Let me not give just the signs. See, I'll just give you two plates alone. So these are two identical plates. So this is negative. So electric field lines, actually, if I drop electric field lines for this negative plate, so electric field lines will be like this in this region. Okay. And in this region, electric field will be like this due to the negative plate, like this. Okay. And what will be the magnitude of this electric field? Sigma y. Okay, now for positive charge, at this place, electric field lines will be like this. Okay. And the value will be sigma y to epsilon 0 again here at this position. Okay. And electric field lines due to positive charge in this region will be also in this direction. So this is again given by sigma y to epsilon 0. So in this region, you can see the electric field produced by both positive and negative charges will be actually additive. So electric field, total electric field will be sigma by 2 epsilon 0 due to negative sigma plus sigma by 2 epsilon 0 due to positive sigma, both actually. Okay. All right. So we are not, okay, let me write due to here also due to minus sigma and due to plus sigma. Both will be actually in the same direction, so they will actually be additive to each other, and then it will provide a strong uniform electric field sigma by to epsilon 0, sigma by epsilon 0, so sigma by epsilon 0. This will be the strong electric field in this region. So So, but what about here at this region? At this region, you know, just outside the plates, see at this particular positions, electric fields due to this positive charges will be in this direction, and for negative charge density, the field lines will be in the same direction. And as I said, all has actually strength sigma to epsilon 0, and you know these two will actually cancel each other and give rise to electric field 0. So this is for due to negative charge density, and this is for positive charge density, CD. Okay, so that's how they will actually cancel each other. Here also for positive charges it will be this direction in this region. Okay, this is for positive charges. Okay, and for negative charges the field lines will be so this side due to negative charges. Okay, due to negative charges it will be in this direction, and these are due to positive charges. Okay, so they will add to again 0. So therefore electric field inside the plates will be uniform, like they will be additive. It will give a strong and uniform electric field, and the magnitude of the electric field will be just addition to that. Okay, that is written in the down. Okay, so written down here, sigma by epsilon 0, sigma by epsilon 0. Okay, I hope there is an okay, this is an option. All right, so this was the second problem. Let us go to the third problem. So third problem, I'll just write it down. Okay, so there is a question. A long solid non-conducting cylinder a long non-conducting cylinder of radius capital R. It charged it charged such that the volume charge density denoted by rho is proportional to R, is proportional to R. So R is the distance from the axis. So where R is the distance from the axis. So we have to find out what the electric field E at a distance small r less than capital R will depend on R, as there are options: E directly proportional to R, V B is E proportional to R square, C is E inversely proportional to R, and D, option D says it is inversely proportional to R square. We have to choose the correct answer. So we have to solve this problem. So the problem is saying that, let me go, yeah. So there is a cylinder. This is solid cylinder. So it will have volume charge density, that is obvious, and it has its original radius. Suppose this is the axis. Radius is capital R, and you have to find out electric field at a distance somewhere here. Okay, at a distance somewhere this place. Okay, at this place, which is R, and this R is less than capital R. This is the force. Okay, so how to solve this problem? Actually, we can use the Gauss's law. We can use Gauss's law. Okay, because for cylindrical charge distribution we will be using. So this can be solved. By using Gauss's law. So what is the Gauss's law? Gauss's law, we know that it will be E into ds, then Q by epsilon 0. Okay. So in this case, Q is not lambda into the length. In this case, it is a little different. Okay. In this case, the total charge is not that. Total charge will be rho into dV. Rho into dV is on the right hand side, and this is also not the length. Okay, this is actually area. So we have to take care of that. Okay, so as you know, we can consider a Gaussian surface. Okay, so actually the rho is directly proportional to R. Sorry, directly proportional to small r. This is what is given, or we can write this as K into R. K is a constant, proportional to constant. Little constant. Okay. So now, first of all, let us write on the left hand side. And okay, before that, let me consider Gaussian surface. So this is the answer part. Consider Gaussian surface. So Gaussian surface, and here let me see, conducting, it is solid non-conducting cylinder. Okay, length, will just take an arbitrary length. Gaussian surface of radius So Gaussian surface means here Gaussian cylinder. Okay. So this is the Gaussian cylinder. Gaussian surface is cylinder. Okay, I'll just Gaussian surface of radius r plus dr. R plus dr. So dr is somewhere. So this is, see, I have to take a cylinder which is passing through r, but this cylinder has some thickness because it is solid sphere. So this thickness is actually dr. Okay, I have to take a thick cell, actually thick cell, cylindrical cell. Thick, here it is actually thick cylindrical cell. Thick cylindrical cell. Okay, Gaussian surface. So what will be the area? Suppose this length is, this Gaussian cylinder has length L. So what will be the surface ds here? And electric field, as you know, you have to consider constant, at least for that particular position. Okay, electric field has to be constant at that particular. No, I'm sorry, not constant. I mean to say it is at this position. So we have to, yes, for Gaussian surface at this particular distance, the electric field will be always constant. Okay, at this particular radius. So the electric field could be taken out from this integration. So this is closed surface. This is ds is equal to, so dq by epsilon 0 for small this cylindrical cell. Okay, so I can write this E ds. This is the area of the small cylindrical cell, and this is actually dq by epsilon 0. So now what is ds? ds is, as usual, 2 pi r l. Okay, this is the ds. But what about dv? Because this is dq, I can write rho into dv by epsilon 0. What is this dv? Or directly we will write dq. dq is rho into dv. Rho is given as kr, and what is dv? dv in this case will be pi r square into l. Okay, pi r square into l. Here actually pi r square, instead of writing pi r square, since it is cell, we have taken thick cell, we have to write this as 2 pi r dr into l. Okay, 2 pi r dr into l. Okay, 2 pi r dr into l into l. So this is actually the volume. Okay, this is the dv. All right, so what you get here, see, you get 2k pi r square. Okay, this is l into dr. So this is actually the dq, the charge. All right, so let me just write down E ds is 2 pi r into l, and dq is actually, see here also, to get the total charge q, I have to do the integration part. Okay, dq by epsilon 0. Okay, so this epsilon 0 is fine. So this is r, small r 0 to capital. So okay, here actually it will be small r only, r equal to 0 to small r. And you know this this has got 2 pi k l r square and dr. All right, so 2 pi k l by epsilon naught, this is r square into dr. So this integration I have to do 2 pi k l by epsilon naught, and this will be r cube by 3. So this will come as 2 pi KL by 3 epsilon 0 into R cube, and here it is E. This is 0 to R, and in fact this side, this is the area, so I can write it is like this itself: 2 pi R into L, 2 pi R into L, 2 pi R into L. So E will be, say, 2 pi L, 2 pi L I can strike out, and this R can be striken out, and written this is R square. So it is K R square by 3 epsilon 0. K R square by 3 epsilon 0. Okay, so this is proportionality constant. These are also constants, so I can say this E is directly proportional to the square of the distance R inside. So let us see whether there are options on that. Okay, so this is the option B. So the option B is the correct answer for this question. Okay. So I hope you have got this point. The only tricky point was that how to get the total charge enclosed by that Gaussian surface. Here you have to take a thick cylindrical shell, as I said, and the area of the thick cylindrical shell has to be written 2 pi r dr into. So this is actually the area of thick cell, area of thick cell. Okay, and if you multiply L, then you will get the volume. Okay, so this was the tricky part. You need to remember this. Okay, so we'll go to the next problem. Okay, so let us solve this problem. A hollow cylinder, a hollow a hollow cylinder has a charge q coulomb within it. If phi be the electric flux in unit voltmeter associated associated with the curved surface B. Okay, I'll just draw the figure. So this curved surface is B, this is A, and this is C. Okay. Then the flask linked with the plane surface A in unit voltmeter will be, I have options for that. One is pi by 3. The option is q by epsilon 0 minus 5. Option option C is q by 2 epsilon 0, and option D is half q by epsilon 0 minus 5. So these are the options. The question is, a hollow cylinder has a charge q coulomb within it. Okay, 5 is the flux, electric flux linked in unit voltmeter associated with the curved surface B. Then the flux linked with the plane surfaces A and B will be how much? Okay, this is the question. So you have to answer for this. Okay, so see here I can say one thing. Total flux associated with this, you have to find the flux associated with the plane surfaces. Okay, associated with the plane surfaces. So let me go to the next page. So I have, see, for a cylinder I have 3 surfaces. Okay, 2 plane surfaces. Sorry, this is C, say, and this is A, this is B. See, if I have a charge here, the flux will be going through this, and going out of this also. Okay, so total flux can be written as this. The total flux will be phi A plus phi B plus phi C. Right. Now phi B is given. Phi B is given as phi. See, phi A and phi C will be always equal to each other. Okay. So I can write. So I can write this as 2 phi A. Oh, sorry. Just a minute. Okay. So I can then write the total part. If this is the thing, then I can write 2 phi A here plus B. In place of B, I will write phi. Okay. So this is the one. Now look, this total phi. Total phi will be anyway given by Gauss's law. Total flux will be q by epsilon 0, right? So this is just simple Gauss's law. Okay, this is from Gauss's law. Phi total will be q by epsilon 0. So I can write this as, see, this phi total as q by epsilon 0, q by epsilon 0, and I have 2 phi A plus phi. Okay, so this could be, so I have to find out phi A. So this is q by epsilon 0 minus phi. This is with half. Okay, so this is the answer actually. So phi A means phi C. So the phi, the flux through the plane surfaces will be half into q by epsilon 0 minus phi. So this was so simple. Okay, we'll just try to take one more quickly. One more quick question we'll take. Okay, so the electric field in a certain region in a certain region is acting radially outward and is given by E is equal to AR, where A is a constant, or A, okay, A is a constant, okay. Now a charge contained in a sphere of radius A centered at origin of the field will be given by option A is A epsilon 0 A square, option B is 4 pi epsilon naught A cube, option C is epsilon naught A cube, option D is 4 pi epsilon naught A square. So what is the question? Question is that electric field in a certain region is acting radially outward and is given by this: a charge contained in a sphere of radius A centered at origin of the field. Okay, let me just tell you this thing. So suppose this is a region and this is the sphere, okay, sphere of radius R, sorry, radius A. This is a sphere of radius A which is placed, so this is the center, this is A, which is placed at the region where the electric field actually is given as A into R. AR. A is the constant set. So what will be the charge contained within this? So if we use the Gauss's law, we know E ds, okay, E ds is equal to charge enclosed divided by epsilon 0. So we can apply here also the same thing. So here it is AR is the electric field, and this will be 4. Actually, we need to just take care of this as see area, you know, I can just directly write this area. I can just directly write that 4 pi a square. Okay, I can write 4 pi a square, and this also I can write A. Okay, 4 pi a into a square, and this as q by epsilon 0. So from here I can directly write the answer. Okay, what is the charge contained in that? Charge contained in that is A epsilon 4 pi a epsilon naught into a cube. 4 pi a epsilon naught into a cube. So let me just show you the option. See, 4 pi epsilon naught a cube. So B, option B will be the correct answer for this question. Okay, so for today we'll be stopping here, and the next class we'll be discussing about further few theory part of this electrostatics, like conductors, insulators, etc. Insulators, etc. Okay, all right. So thank you for your patience. Bye for today.